Hi, my name is Cole McCullough, and today I'm going to be using coding to solve one-dimensional heat transfer problems. So the first problem that we're looking at, we have a brick wall that is 0.5 meters wide, and it's at a uniform temperature of 300 Kelvin. It's given an alpha value or a thermal diffusivity value of 4.72 times 10 to the negative 7th meters squared per second. So what we want to do is heat and maintain the sides of our walls at 425 Kelvin and 600 Kelvin. And what we want to find out is how long it'll take until the center of the wall reaches 425 degrees Kelvin. So this is the equation that we're going to use to solve this. We're going to derive it to solve for T sub I at T plus delta T. And we can use our thermal diffusivity given, our temperature, time, and position to solve for all these. So you notice we're not giving a time, that's what we're solving for. So what we have to do is get an Excel file and do multiple iterations, computing this formula over and over again until we get the 425 degrees Kelvin needed. So real quick, I just want to talk about stability criteria. What we're doing in one dimension, the stability criteria is alpha times delta time over delta x squared, and we want that to be less than or equal to 1/2. In our case, it would be exactly 1/2. However, in two dimensions, we'll have a very similar equation, except it's going to be less than or equal to 1/4. So the textbook doesn't explicitly say what a third dimension equation would look like, but since 1/4 is 1/2 squared, I would assume that it would be 1/8 because that is 1/2 to the third, and I'm sure it would be a very similar equation. So before we go into the second problem, I want to show this Excel file, and this is it, and we have all the variables given. Our dx is not 0.5 meters, it's our iterations, and we go until we have the 0.5 meters, but they're 0.025 meters apart. We have a delta time, which is 662 seconds, and it's that long because it'd be a long period of time before the middle gets to that 425 degrees. And these make an exact value, a stability value of 0.5, and we have our alpha value of 4.72 times 10 to the negative 7th. So as you can see, each iteration, it goes a little bit closer to the middle. So the middle isn't changed until about the 15th or 16th iteration or so. So if we were to do this perfectly, we would have our delta t at an infinitely small time. But that would just take tons of iterations and wouldn't be very practical. But I found the Excel file interesting because it slowly gets to changing the middle, and then for a long period of time, we're just slowly heating it up until we finally get to our 425 degrees Celsius. So we had to divide our time by 3600 because it was initially in seconds and we wanted it in hours. And it takes about 17 hours to get that final temperature of 425 degrees in the center. So now that we have our answer to the problem, we wanted to do a plot of the temperature versus position. And we wanted to kind of animate to show it over time. What we had to do for this is we had to write a VBA code. And I chose to do VBA because I thought it would communicate better with the Excel file. And the Python file that I was working with, it had a tough time importing the data from the Excel. So I thought that VBA would have a better communication with the Excel data and would, in the end, be able to create a better plot. So looking at this VBA, we start off with a bunch of stuff that doesn't look too familiar to the average VBA user. And all this is this is necessary to use the sleep function that we're going to look at later on. But I created a subfunction called animate, had to set a few variables with the dim function. We set our chart to be the chart that we choose. We already had a chart on there that is set at the initial 300 Kelvin for the entire wall. We set a variable at x equals 1. X is just a counting variable that we'll use later on. And then we have this thing that doesn't look too familiar. is application.screen updating equals false. And the sole reason for that is next we're going to do a loop that will essentially just count how many iterations we did. And it turns out to be around 100 iterations or so. But we have this as false because we don't want it to update the screen while it's going through this piece of code. And the reason for this is because we don't need it to update. And if it's not updating, then it's going to go faster. We're still getting our values to update, but the screen will not update. But then we're going to want to turn it back on because we want it to update once we get our animation going. Because if this was still at false, then it would just show the end of the animation. So the actual thing that what we're doing to change the values in the chart is we're having the chart series collection, and this is our chart dot values, and basically we have it go down one each time, and we'll show each iteration of y values are the temperature values. So the sleep function that I was talking about a little earlier, it basically pauses the sub function and lets the screen display it so we can see that animation, but only if we do this do events call right after. And the next in, that means it's going to go through each iteration that we have and keep on going until the end. So let's see this in action. We're going to just press this button called animate because that's what we're doing. And we can see initially we're at that 300 Kelvin that the problem said we started at. But once we press this, we're going to go to our side values that we were told, and we're going to keep getting closer and closer to that middle being at 425 degrees Kelvin. So starting it, you can see it's at about 350 right now, keeps on going and going, and got to about 425 Kelvin, and then we're going back to the end. So let's see it again. So yeah, as you can see, the center got to 425 Kelvin, and let's just keep pressing the animate over and over again, so we can see the heating in place, the heat transfer in place, and can see over those 17 hours how it's gradually rising in the middle until that 425 Kelvin. So now we're going to look at this next problem. So this was a problem that we chose that's pretty similar. We have another brick wall, and we're giving the thickness of it at 30 centimeters. We're given the height and length of it at, width of it at 4 meters, 7 meters, so we can calculate the area. We're given the thermal conductivity and the temperatures on each side. So what we want to do is determine the rate of heat transfer through the wall in watts. And we were given all these variables, and this is the equation that we'll need to take care of it, where we were given that thermal conductivity. We're able to calculate our area with that width and height. We're given the length, and that's the thickness that we were told, and the temperature, and this is going to calculate our heat transfer. So let's go to the Python file. All the variables that were needed, length, K, T1, T2, width, height, and we have our formula for area. And we're going to stick all that into our negative Ka times T2 minus T1 over the length. And after that, we're just going to print out whatever is computed in this Q, and it turns out to be 1159.2, and that's going to be in watts. So that is all that I have for you today. As you can see, we use both Python and VBA with a little help from Excel to determine these problems and show a model for the heat conduction over a period of time. Thank you.